Okay, our next speaker is Haoyuan Wang, and he comes to us. He's a PhD student at UC Santa Cruz, and his interests are RTL simulation, computer architecture, and parallel computing. And he is going to give a talk on RepCut, superlinear parallel RTL simulation with replication-aided partitioning. So take it away, Haoyuan.
Okay. Thanks for introduction, and also thanks for interest in my talk. Today I'm going to introduce our recent work, RepCut superlinear parallel RTL simulation with replication-aided partitioning. My name is Haoyuan from UC Santa Cruz. Hardware simulation is a fundamental tool for SoC development, debugging, and validation. It basically translates HDL code to functional equivalent C or C++ code. However, the slow speed of simulation limits coverage and design iteration. This problem is becoming more and more severe as the complexity of IC design has quickly reached a point that the full coverage cannot be completed within the development schedule. So naturally, parallel RTL simulation seems to be a viable solution to achieve even higher simulation performance. However, despite the parallel nature of circuits, parallel RTL simulation has been proving challenging for decades. Existing work shows limited scalability and achieves only sublinear speedup. The sublinear speedup makes parallel RTL simulation unattractive in production environment as it would reduce overall simulation throughput. So we identify the challenge of parallel RTL simulation as work allocation. In this work, we choose the state-of-art open source simulator Verliator as an example. Verliator creates many partitions by splitting circuits at the dependency, and those partitions will then be mapped to worker threads by a static scheduler. The data dependency would require some thread synchronization and ultimately the thread store. The profile information here suggests the following performance limiter. Firstly, the frequent thread synchronization would lead to thread stall. As we can observe, there are many bubbles inside the heat map. And secondly, perhaps the more severe is that there exist few huge partitions that are way too large to create a balanced scheduling. So how does RepCut solve those problems? Well, RepCut greatly reduces data dependency by replicating small fragments of circuits and cut the circuit into disconnected partitions, which yields the name RepCut. And it creates a much more balanced partition by more accurate execution time prediction. In terms of implementation, RepCut has only one synchronization per simulated cycle, and which significantly reduces synchronization overhead, and each partition is mapped to one thread, minimize scheduling overhead. Compared with Verliator that has a frequent thread store and highly imbalanced, profile information shows that RepCut has a much higher CPU utilization and fewer wasted cycles. So how do we partition the circuit? Before we start partitioning, we first cut the input circuit at the register and memory boundaries. This is actually explored by many previous work. However, this step generally doesn't yield balanced partition. Instead, in our experiments, in most situations, it only yields one huge partition with few circuit fragments. Our main motivation of splitting register and the memory is to significantly reduce the circuit connectivity. After splitting at register memory and memory boundaries, RepCut generates an intersection hypergraph that represents the intersection relationship of cones. By doing so, RepCut converts the problem of using replication to partition into a hypergraph partitioning problem. The later one is known to be NP hard, but actually compared with the previous one is well studied. RepCut uses state-of-art hypergraph partitioner to partition the intersection hypergraph into disconnected partitions. Please read our paper for more information, as we are unable to introduce much. We are unable to introduce much details in such a short talk. RepCut is implemented as an extension of Ascent, which is also mentioned in previous talk. And we disable the circuit activity optimization, which means the RepCut is a full cycle simulator. And for comparison, we use Replication-Aided, which is a state-of-art open source high-performance RTL simulator, which has similar or better performance compared with commercial RTL simulators. We also enable the Replicator's profile-guided optimization, which provides the Replicator's scheduler and accurate execution time information collected from profile. Replicator without PGO is not shown here due to page limitation. We choose two open source parameterizable RISC file processors as a benchmark. First one, Rocket chip, which is an in-order core, and Boom, which is an out-of-order core. We take 4 configurations with size increasing from the default Rocket chip to small boom, large boom, and mega boom. And the number of simulated cores increases from 1 to 4. We're using Clone version 10 with O3 as our compiler. Since we are working on parallelization, the first one we are interested in the self-relative speed up or the scalability. As we can see here, from left to the right, the design size increases from rocket chip to small boom, large boom, and mega boom. From up to the bottom, we have the number of simulated cores increase from 1 to 4. It's not hard for us to observe that for smaller designs like single core rocket chip, RepCut has similar speed up compared with Replicator. However, as design size increases, RepCut quickly outperforms Replicator and with the PGO and achieves linear or superlinear parallel speed up. The red line here is the linear line. Replicator's PGO provide minor performance improvement as as there are a few gigantic partitions that prevent Replicator from getting any performance benefits from PGO data. The absolute performance or simulation speed is another key aspect. Like previous slides, the design size increase from left to right and from up to bottom. It's not hard to notice that RepCut has has different single thread performance with Replicator, and as they have different baseline implementation. And the single thread performance of RepCut in small design is faster than Replicator, as shown on the left-hand side, but slightly slower on larger designs. However, RepCut's better scalability makes it quickly outperforms Replicator when using more threads for simulation, and it achieves best multi-threading simulation performance on any of the tested designs. The peak performance is achieved by RepCut using on single core rocket chip, which is the smallest design, and achieving 150 kilohertz using 6 threads. As we are removing synchronization at the cost of extra computation, and naturally the amount of extra work is a major concern. We measure the extra computation as replication cost, showing in this figure. There are 4 subfigures shows replication cost of rocket chip, small boom, large boom, and mega boom. And in each subfigure, 3 lines representing 1, 2, and 4 simulated cores. From each single line, we can observe that the replication cost increases with the number of simulated threads or partitions, and the replication cost reduces for larger designs. More specifically, the largest design, 4-core mega boom, has a replication cost of only 3.81 when partitioned to 24 threads. In overall, the replication cost is noticeable, but definitely worthwhile if we consider the performance gain. So how does RepCut achieve superlinear speedup? Firstly, it creates much balanced partitions with only 1 synchronization per cycle, which greatly reduces CPU cycle waste. And secondly, by using more threads, we are actually distributing smaller code to each core. The smaller code footprint reduces the pressure of processor front-end components like branch predictor and cache, and finally leads to better IPC. So the superlinear speedup is reasonable if we consider that IPC doubles from 0.41 on single thread to 0.95 on 24 threads. We can also observe a significant decrease on branch miss rate and cache misses. In conclusion, in this work, we introduced RepCut, which achieves superlinear parallel RTL simulation on large complex designs like modern out-of-order processors. and we propose a novel partitioning scheme, and we exploit the optimization opportunities that emerge from the reduced synchronization context. Such a superlinear speedup makes parallel RTL simulation an attractive option in production, as both individual simulation as well as overall simulation throughput could benefit. Please check our paper for more information. And RepCut is open source under BSD license, and the result is reproduced by anonymous peers. I would be happy if anyone has any questions. Thanks.